Hi, it's my pleasure to present my work, the process-aware cache-oblivious algorithm, to you. Our motivation is Frigo et al. Proposed an ideal cache model and a recursive technique to design sequential cache-efficient algorithm on a hierarchical architecture of caches in a cache-oblivious fashion. There are two open problems with it. Firstly, portability. That is, how to extend the technique to an arbitrary architecture, including the distributed memory architecture or heterogeneous architecture. Secondly, scalability. That is, how to run an efficient algorithm, say Strasson's algorithm, exactly and efficiently on an arbitrary number of processes. By exactly and efficiently, we mean it should attain communication law bound exactly and attaining communication law bound up to a constant factor. There are two classical ways of extension in the literature. Firstly, process oblivious. This approach only specifies data dependencies of the algorithm and leave an efficient runtime parallelization to a runtime scheduler or folding mechanism. The inputs of the algorithm is sequential cache complexity and its critical path length. It relies on a runtime scheduler if it's on a shared memory machine, or a folding mechanism if it's on a distributed memory machine. Then it outputs the parallel complexity bounds. The main benefits of the approach is it's easier of programming. It's more adaptive to non-dedicated settings, that is, if it's running together with some other applications. And it's scalable to an arbitrary number of processes. The main problem of it is it usually incurs more communication overheads than a PA counterpart. It may require to choose a proper base case size. Fundamentally, the problem is due to the runtime scheduler has no knowledge of the algorithm. Another approach of extension is process-aware. It calculates the work and time complexity bounds along a critical path. The main benefits is it usually has better performance in both theory and practice. The main concern is an algorithm may require the process count P to be factorizable into 2 or 3 roughly equal numbers. The Cache-Oblivious algorithm requires that P to be an exact power of 7. So later, Lipschitz et al. Improved P to be a multiple of 7 with no large prime factors. Our contribution is we proposed a novel process-aware but cache-oblivious way of partitioning a cache-oblivious algorithm to achieve perfect strong scaling based on a pruned BFS traversal of the algorithm divide-conquer tree. The application include, but not limited to, LCS, 1D, GAP. They are all dynamic programming algorithms, general matrix multiplication, Strasson's algorithm, triangular system solver, Cholesky, LU with partial pivoting, QR factorization, and comparison-based sorting. Our work works on shared memory, distributed memory, and heterogeneous computing systems. Our solution provides an almost exact solution to the open problem on parallelization Strasson exactly and efficiently on an arbitrary number of processes. It also provides a new perspective on the open problem on extending the recursive cache-oblivious technique to an arbitrary architecture. Our computational model is a DAC. The vertex is a piece of computation with no parallel constructor. Each arithmetic operation is counted uniformly as an O1 operation. The edge counts the data dependencies among vertices. We don't count control dependencies because the control dependencies can be possibly removed by some data flow model. Our machine model is the ideal distributed cache model, which was proposed by Frigo and Strappen. It has P dedicated processors with identical performance. It has 2-level memory model as shown on the right-hand side of the slide. We assume that the cache is a non-interfering private cache. That means the cache misses of each processor can be analyzed independently. We do not consider cache coherence protocol or fault sharing. None of our algorithms have data races. A general PACO algorithm is as follows. A sequential cache-oblivious algorithm can be viewed as a DFS, that is, depth-first traversal of the algorithm divide-conquer tree. A parallel one is usually some interleaving of DFS and BFS traversal of the same tree. It usually uses DFS traversal to reduce memory footprint of a task, and use BFS to increase the parallelism. A PACO algorithm is then a pruned BFS traversal of the same tree. Our basic observation is the maximum speedup attainable on a p-processor system is usually p folds. So firstly, it unfolds the algorithm C-way divide-conquer tree depth by depth in a BF fashion. The C is an algorithm-specific constant. For example, in the classical matrix multiplication algorithm, the C is 2, and in a Strasson's algorithm, the C is 7. If some depth has larger than or equal p ready nodes, up to c-1 times p of them will be pruned, that is, will be executed sequentially, that is, a DFS on a assigned processor. The rest of nodes will go to more rounds of pruned BFS traversal. This procedure will repeat until either all nodes are pruned or all nodes are base cases, in which case all of them will be assigned to all processors in a round-robin fashion. On the right-hand side is a picture of pruned BFS traversal of a binary tree, assuming the process count is 3. The label indicates assigned order. The invariance of a PACO algorithm is that we partition all nodes into p sets. Each set forms a geometrically decreasing sequence in terms of both computation and communication, and usually the top nodes dominate. So we just count the top nodes is enough to count the computation and communication overheads. Compared with classic PO approach, which divides each and every node to base cases to increase the slackness. But usually more slackness means more potential deviations from sequential execution order. Thus, it will incur more communication and synchronization overheads. Compared with classical PA approach, it is usually constrained by the structure of algorithm. For example, the Cache-Oblivious algorithm requires a p process count to be an exact power of 7, though later it was improved to a multiple of 7 with no large prime factor by a hybrid of Strasson and classical matrix multiplication algorithm. 2D, 2.5D, and 3D matrix multiplication algorithm requires p to be factorizable into 2 or 3 roughly equal numbers. We count the complexity of a PACO algorithm as follows. It assumes non-interfering cache, so all tasks can be counted independently. We also have a more formal and more restricted perfect strong scaling property, which was initiated by Blood et al. It assumes optimum balanced computation and optimum balanced communication. By the property, the overall quantity should be asymptotically optimal, and the quantity along critical paths should be exactly 1 over p of the overall quantity. The difference between processes, if any, cannot be more than an asymptotically smaller term, and the property should be valid for an arbitrary number of processes. Our PACO MM algorithm and PACO Strasson algorithm is basically a pruned BFS traversal of corresponding divide-conquer tree. The PACO MM algorithm is a 2-way divide-conquer tree, and PACO Strasson is a 7-way. And the divide-conquer tree are of the sequential divide-conquer algorithm. If associating the root of the tree with p processors and dividing a node with p prime processors by the ratio of p prime over 2, the floor over the ceiling of the p prime over 2, then we have the PACO MM one piece of it. Then each set of a processor has only one piece of cube to compute. If we stop the traversal after some constant number of rounds, then we have PACO-Strassen constant piece algorithms. We can also extend the approach to distributed memory settings and heterogeneous settings. We have made some preliminary experiments on our PACO MM1-piece algorithm. Because we want to compare only the difference in partitioning and scheduling, we require that all algorithms of the same problem call the same kernel functions to compute sequentially based cases. In our final running time, we include all partitioning and scheduling overheads. We measure running time as a mean of at least 3 independent runs to avoid averaging noises. And the following is the way we count the speedup and Rmax and Rpeak. The Rmax is the performance we have achieved in our PACO MM1-piece algorithm. The Rpeak is the theoretical peak performance of our machine. Our machine is a 24-core machine. And we can see in this slide that our PACO MM1-piece algorithm does have some performance advantage over Intel's MKL on the Intel machine. In our experiments, the problem size is calculated as n times m times k, where n and k iterate independently from 8,000 to 44,000 with a step size of 4,000. The n and k are 3 dimensions of the matrix multiplication. On the 24-core machine, the mean and median speedup of our algorithm over Intel's MKL is 11.1% and 60.4% respectively. Compared with a classical PO algorithm, our approach doesn't need to tune, which is an advantage in practice. Conclusion: we propose a general PACO algorithms based on a pruned BF traversal of a Cache-Oblivious algorithm's divide-conquer tree. We have application to several important Cache-Oblivious algorithms. Compared to classical PA approach, our algorithms achieve perfect strong scaling on an arbitrary number of processors, even a prime number of processors within certain range. Compared with classical PO approach, our algorithms usually have better communication complexities and doesn't need to tune. Our PACO-Strassen constant piece algorithm provides an almost exact solution to the open problem on parallelizing Strassen's algorithm efficiently and exactly on an arbitrary number of processors. We also discussed the extension to distributed memory and heterogeneous settings. Our approach may provide a new perspective on the fundamental open problem of extending the recursive cache-based technique to an arbitrary architecture. Question. Thank you.